The chapter 2 of your textbook is about the limit and the derivative. Actually, how do algebra and the calculus differ? The two words, static and the dynamic, probably come as close as any to expressing the difference between the two disciplines, algebra and the calculus. In algebra, we solve equations for a particular value of a variable, which is a static notion. In calculus, we are interested in how a change in one variable affects another variable, which is a dynamic notion. Isaac Newton and Wilhelm Leibniz developed calculus independently. One of them are English, one of them is German scientist, to solve problems concerning motion. So from physical problem, the calculus was developed. Today, calculus is used not just in the physical science, but also in business, economy, life science, and social science, and any other discipline that seeks to understand dynamic phenomena, like this course actually. In chapter 2, we introduced derivative, one of the two key concepts of calculus. The second is the integral, is the subject of the chapter 5, which is the topics of the second term. Both key concepts depends on the notation of limit, which is explained in the first section of this chapter, and second section also. We consider many applications of limits and derivatives. Basic to the study of calculus is the concept of limit. So the section 2.1 is Introduction to Limits. This concept helps us to describe in a precise way the behavior of the f of x when x is close but not equal to a particular value c. In this section, we develop an intuitive and informal approach to evaluating limit. The formal approach is include more maths, so because of that reason, I will not give the formal definition of limit to you. In the chapter 1, we have already learned the graph of the function. Actually, we learned the point-by-point graphing idea. The graph of the function f of x equals x plus 2, you can sketch easily. Like the following one, this one. X-intercept is 2, x-intercept is minus 2, y-intercept is 2. So this is the graph of y equals x plus 2, or graph of the function f of x equals x plus 2. So let's write graph of f of x equals x plus 2. From here you can see several things. Actually we know that. So for example, when x equals 0, y is 2. When y is 0, x is minus 2, etc. Or for another values, for example, when x equals 1, you can find the y value as a 3, or when x equals -1, the x value is 1, y value is 1, sorry. So here the domain value -1, 0, 1, etc. are associated with the x-axis, and the range value, the value of the f of -1, which is 1, the f of 0, which is 2, f of 1 is 3. So these are associated with the y-axis actually. Okay, so we know that f of -1 is 1, -1 plus 2, which is 1. F of 0 is 2. F of 1 is 3. So all of these values associated with the y value. Now I introduced the important concept of a limit through the example, which leads to an intuitive definition of the concept. So let's consider the function f of x equals x plus 2 graph. We will discuss the behavior of the value of f of x when x is close to the point 2. Okay, so here this is the point 2. Let's use red color. Clearly the function value is 4. We are sure f of 2 equals 4. But our aim is to observe the behavior when x is close to 2. Okay. Let's observe the some values by using the green color, which is close to the 2. So for example, for this point, this is the function value. So if the that point approach to point 2, okay, it approached to point 2. For example, for this point, you can make this observation. The value is that point. Okay? The value is this point. So when this point approach to 2 from right side, the values approach to 4 from the upside. Okay, bigger values of the 2 for this function. So here, for the another point, we can make this observation. So approach to the function will approach to 4 from right side. Okay, and from the left side, for example, for this point, the function value is that one. When we approach to 2 from left side, this approach to 4 again. For that point, again we approach to 4. So what that means? This graph shows us when x get closer and closer to 2, the value of the f of x get closer and closer to the 4. So this situation written mathematically by the following way: limit when x goes to f of x equals 4. This equation, this equality, this equation is read as the limit of f of x, x approach to is 4. Note that f of 2 is 4. There is no problem. That is the value of the function at 2 and the limit of the function as x approach 2 are the same. In the future, this situation will be called as a continuity at the given point. So this expression can be expressed by the following way, which equals f of 2. Okay, so limit and the function value are the same, which is the 4. Graphically, this means that there is no hole or break in the graph of f of x at x equals 2. Now, I can give the definition of limit. we write limit when x goes c f of x equals L, or sometimes we use the next notation f of x goes L when x goes c. If the function value f of x is close to the single, this is important, single real value or real number. Okay, your textbook says number, real number, capital L, whenever x is close but not equal to the value c. On the both side of the, on either side of c. Please note that the existence of a limit at c has nothing to do with the value of the function at c. In fact, c may not even be in the domain of f. However, the function must be defined on the both sides of the c. So you can talk about the limit of the function f as x goes c, or at the point c you can mention. I think that everybody knows the absolute value function. The absolute value function is can be defined as the following way. If x is negative, this is minus x. Since x is negative, that value is positive. If x is bigger than 0 and 0, this is x. Okay, this is the absolute value function. And the graph of the absolute value function likes that one. These two lines. This is graph of the f of x equals absolute value of the x function. Of course, somebody can say that right hand side equals y equals x line, left side is y equals minus x line. Okay. So by using the absolute value function, I would like to give an example. Please consider the following function: absolute value of the x over x. And now we explore the behavior of the f of x for x near but not equal to 0. So we will calculate the following limit. Our problem is limit when x goes to 0. What is the h of x? The function s is defined for all real number except 0. H of 0 is indefinite because of denominator, okay? Because we have 0 over 0 undefined case, okay? But so the domain of the h is all real number except 0. So you can calculate all value for h except 0. Note that if x is any negative number, if x is negative number, h of x equals absolute value of the x over x. Absolute value of the x is minus x, so minus x over x, so which is 1. If x is positive number and 0, not 0, it cannot be 0, sorry. H of x is absolute value of the x over x. Absolute value of the x is itself equal x, so x over x, which is 1. So the graph of the h of x function, like that graph, which is always 1 if x is bigger than 0. If x is less than 0, this is always minus 1. So we use the empty point here. It's not full point, okay? Inside is empty because at the point 0 function is not definite, not the 1 or minus 1 or another value because it is undefinite. So this is the graph of this function. So when x approaching 0, this is the point 0. So for the left point, function value is minus 1. So here minus 1, minus 1. So from the left side of the 0, it has always minus 1. From right side of the 0, when we approach to 0, function value is 1. So there is no unique limit point, okay? So limit when x going to 0, h of x does not exist. Why? When x is near 0 from left side, limit is minus 1. When x is close to the point 0 from right side, that is limit is 1. And these are not equal, so there is no limit. In this example, we see that the value of the function h of x approach two different numbers, depending on the direction of the approach. And it is natural to refer to this value as the limit from left and the limit from the right. This experience suggests that the notation of one-sided limit will be very useful in discussing basic concepts. So, we are ready to define the one-side limit. We write limit x goes c from left side, f of x equals capital K. Okay, here maybe we can emphasize x goes c from minus from left side. This means is read x approach c from the left. And it means x goes c but bigger than c. So this means x goes c and x is less than c, yes, but from left side. This limit and call K the limit from the left or left hand limit if f of x is close to the key whenever x is close to c on the real number line. Okay, so key is the limit from the left, so it is called limit from the left. Sometimes I said and sometimes we say left limit, okay, the left limit. And similarly, limit x goes c from right hand side, we denote by that way, f of x equals f. Similarly, that means x goes from c to positive is read x approach c from the right. Mathematically, that means x approach c and x is bigger than c. And here L is limit from right. Now, we can put the relation between the limit and the one-sided limit. Actually, this is the definition of the one-sided limit. So we have an important theorem for a two-sided limit. Actually means for a limit to exist the limit from the left, sorry, and the right must exist and have to be equal. That is, mathematically we can denote limit x goes c f of x equals L if and only if limit x goes c from left side equals limit of the function f of x when x goes c from right hand side, and which is the L.